guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the thermal contact resistance in heat transfer. So just an overview of what we're going to discuss. We're first going to look at the distinction between a series and parallel thermal contact resistance. We'll then take a look at the interface junction in a lot more detail. We'll then see how to model and then perform an energy balance analysis on the system. And then we'll bring it all together and we'll solve a working example. So the first thing that we want to identify is what exactly is a thermal contact resistance? Well, in simple terms, it's essentially the ratio between a given temperature drop and the average heat flow across the interface with two objects in contact with each other. Now, how we can express this usually is in the form of Q, so that is the average heat flow is equal to the change in the temperature divided by the summation of all the resistances. And so that would be our thermal contact resistance. But what we have to be careful of is within a given system, there is usually more than one resistance. So this summation of R is actually the total thermal resistance. The contact resistance would be at the junction where the materials meet. So that's the key distinction that we have to account for. So this delta I, so the summation of R, is of two key components, and we'll see what these key components are in just a second. But what we want to do is just recap on the three different types of thermal resistance and what the respective equations are. So we have conduction, which is essentially the length of the material. Now sometimes this is denoted by X, but here we're going to use the letter L, and that is L over K, which is the thermal conductivity of the material, multiplied by A. Now we can also have for convection, whereby we have 1 over H multiplied by A, where H is the film heat transfer coefficient for that given fluid, and A, of course, is the surface area. And then we have the radiative resistance, which again is 1 over the radiative heat transfer coefficient of the fluid, multiplied by the surface area. Now it is worth noting that these equations can also be expressed independently of the area. And so rather than it being Kelvin per watt, it would be written as Kelvin per watt meter squared. Now when we talk about a network diagram, one of the ways that we can represent these resistances is, you may have seen this before, is we usually start with, say this was T1, and then we have the resistance, and then this will become T2. So this expression here is how on a network diagram we represent the resistance. So say this was for conduction, we would usually have T1, T2, and then we would say L over K A if we wanted. And so just in case you come across this and how you actually read it, this is how you express the resistance on a network diagram. So if we take a look at the distinction between contact resistance in parallel and in series, then the contact resistance in parallel is essentially expressed as the summation of the inverse of the resistance. Now what does that mean? Well, in simple terms, if we imagine we have Q coming in, so that's our heat flow coming in, and then we have our heat flow coming out of the material, then what you can see here is that we will have a change in the amount of Q for material A, which is the blue material, material B, which is the orange, and then we have our contact, which is in this section here. Now, because the direction is the same for A and B, in that we will have some form of resistance because of the thermal conductivity of A, some resistance for the thermal conductivity of B. Now, if these are different, then the change in the temperature profile will be different. So what does this actually look like on a graph? Now remember, it is the inverse of the resistance, and so we have X and we have T. So X is on the y-axis, T is on the x-axis. X being our distance. So we can sometimes call it as L as well, it just depends. Now what's going to happen is that, imagine this is the hot section and this is the cold section. So we're going to lose some amount of Q as we progress from point 1 to point 2. Now what that would look like is a change in the temperature. As we move through the distance, we will have this decrease in temperature. Now the steepness of the line is of course dependent on the thermal properties of that given material. So this is just a very generic example. Now the change which is responsible for the thermal resistance is actually quite small. So we don't see a large change in the temperature. And that's because the resistance due to the contact is significantly smaller than those of the material. It doesn't play a huge part because we're working in parallel. We'll see the key distinction when we look at the one in series. And then of course we're going to move more steeply depending on the thermal properties of material B. But the key thing that we want to highlight is the steepness of the contact resistance. And so in the case of parallel, that does not play a very large role in the resistance. Whereas if we take a look at it from the perspective of in series, then what we can see here is that Q must go through material A first. Whereas if we come back to in parallel, it will go through A and B at exactly the same time. Whereas for in series, we have to go through one before the other. And so we will pass through material A, then we have the contact resistance, which is here, and then we will go through material B before the amount of the energy flow comes out the other end. Now what does this look like? Well, we'll have our gradient of the difference in the temperature. Now notice this time, temperature is on the y-axis and the distance is on the x-axis. And so as we progress through the distance of x, our temperature will decrease. Now when we get to the contact, notice that the change in the temperature becomes significantly larger. The distance doesn't change because this is just at the point of contact. So there is no real, change in the distance. The key thing here is that we have a consistent and large change in the difference in the temperature. And then of course, if we move through component B, then we get that gradual change in Q as we progress from left to right. So notice the key distinction here is that for in series, the contact resistance is significantly higher than that in parallel. Now if we look at the interface junction in a bit more detail, so when we depict, so in this case, when we look at this, we often assume that the contact between A and B is perfect. It's so smooth that it is 100% solid to solid contact. But is this a real accurate representation? Well, in actual fact, it's not. And if we focus on this junction, then if we were to look at it under a microscope, we would actually see that there are points where they don't touch through solid to solid interaction, that there's actually these small air pockets. Now, usually they are filled with air, but they could also be, a specific type of gas. It could be nitrogen, it could be, pure oxygen, it could be helium. It just depends. But typically, they are comprised of just normal air. But the key thing that we'll want to highlight here is that the conductance of heat through air is significantly different to that of solid to solids. And so we don't have 100% contact between the two materials. And so our Q actually becomes the heat flow which is associated with the gap, so that is for the fluid, so that's the open space between the system, and then Q for the contact, which is the solid to solid heat transfer. So that is actually what's taking place here at the interface junction, is that it is a combination of both of these terms. Now, the contact we can express further and say that our contact, so QC, is equal to this new variable HC multiplied by the area multiplied by the difference in the temperature at the interface. So it's not the difference in the temperature between this point and this point, it's the difference in the temperature between this point and that point. Now, what is HC? HC is often termed as the contact coefficient or sometimes the conductance. So I'm going to refer to HC as conductance. Now let's take a look at this in a lot more detail so that we can perform an energy balance analysis on the overall system, but also in the interface junction. Because if we understand it from the concept of the energy balance, then we fully understand what is actually going on as we move from point 1 to point 2. So let's stick with the same nomenclature, is that we'll have component A, component B. Now we can see here that we have both solid to solid conduction taking place, but we'll also have conduction through the trapped fluid. And so what this then means is that we have this intermediate set of temperatures. And it's that we have T1, so that would be the Q in, T3 is Q out. Now this T2A and T2B represent the temperature difference at the interface. So that would be delta T interface that we've seen in the previous slide. Now the A and the B simply denote that this is the temperature on material A and this is the temperature on material B. So the difference between these two is the change in temperature at the interface. And so by focusing only on the junction, we aren't going to look at T1 and T3. If we only look at the junction, then the balance would become as follows. It would become the change in the temperatures, because remember, this is the change in the temperature divided by the resistance. And so we'll have T2A minus T2B divided by 1 over HCA. And this A is the area, so the contact surface area. Now notice that at the junction, it's HC. So it is the conductance value. Now we can further expand on this, and we can say that if we break this apart, then we can express this in both the solid to solid conduction plus the convection through the air, the trapped fluid. And that would be that we have T2A minus T2B. So the delta T is going to remain the same. That's not going to change. But the resistance will be slightly different. This is for the solid, where we have the length divided by 2Ka, so that's the thermal conductivity of material A, multiplied by the contact area, so AC, that's for the solid to solid. And then we have the thermal conductivity of the fluid multiplied by the area of the trapped fluid multiplied divided by the length of that contact interface junction. Now the problem here lies is that it's very, very difficult to isolate AC, AV and LG. because these are at the interface junction, and that's why we tend to use only this expression, because HC is a lot easier to obtain from experimental data than to actually identify what AC, AV, and LG actually is. But this is just to highlight exactly what is going on within the system. So this is for the fluid and this is for the solid. This here has the greater influence on the value. Now, one thing to note here is that if we look at this in a bit more detail, then we can determine the conductance through the manipulation of the previous equation here. So we can rearrange all of this to identify what the conductance is. And what that would be is that the conductance is a function, as we says, of AC, of AV, of the length of the gap, and the overall surface area, and then we have our thermal conductivity properties of the solids and the fluids. And as we says, AV, AC, and LG are very, very difficult to isolate. And so what that then means is that we tend to use reference data of HC. Now, there is a free reference table which has several different configurations for conductance for a wide range of materials, both solids and liquids. And so there'll be a link in the description. You can download that for free and use that as you will if you're coming across problems that are associated with conductance. And it's really, really helpful. It gives you the conditions, it gives you the operating parameters, and it will give you the value of conductance. So a really, really powerful reference table there. Now, if we expand on this, and rather than just focusing on the junction, if we look at it from the overall energy balance, then this would then allow us to derive the following equation. We would then know that Q must be equal to the thermal conductivity of material A multiplied by the area, multiplied by the change in the temperatures, divided by the corresponding length. That is fairly simplistic. Now, of course, that then has to be equal to the change in the material at the interface, so that's what we've seen before, must also be equal to the same expression, but this time for component B. And so here we could actually call that B rather than A. And so what this would then allow us to do is bring all of these together and we can simplify it. Because we can see here that minus 2A, T2A, and T2A, they all cancel. And then T2B and T2B cancel. And so what that then allows us to do is show that Q must be equal to the change in T1 minus T3 divided by the 3 resistances. And we can see here that this is the resistance through material A, this is the resistance at the contact at the junction, and then this is the resistance for material B. So you can see how we piece it all together and we derive the overall energy balance for this given system, which is in series. Now, let's take a look at a worked example here. How do we actually go about solving? So the problem that we have here is we've got 2 stainless steel rods which are in contact with each other, and they both have a length of 10 centimeters. And we know that the diameter of each is 3 centimeters, so quite a small rod. Now we're told the thermal conductivity is 16.3 watts per meter Kelvin, and we're also provided with the conductance, so that's the HC value, of 1900 watts per meter squared Kelvin. We're told that the system operates at 50 atmospheres with a difference in the temperature of 100 degrees Celsius. And what we want to do is determine the percentage loss of heat through the system. So we basically have one rod here, we have another rod here, and we want to know what the percent difference is from this point and that point. Now, because the bars are identical, then they're going to have exactly the same resistance. So all we need to do is really find 1 and then multiply it by 2. So the resistance of the bar is going to be through conduction, and so we want the length divided by the thermal conductivity multiplied by the area. And so we just convert everything to SI units. So we'll convert the length from 10 centimeters into meters. So we get 0.1 divided by 16.3 multiplied by the cross-sectional area gives us 8.679 Kelvin per watt. Now for the contact resistance, we can then say that we have 1 over HC multiplied by A. So we were told what the conductance was 1900. We have our area, which gives us 0.744 Kelvin per watt. And then what we can say is that the total resistance is going to be 2 times the resistance of the bar plus the contact resistance. And so we would just do 2 multiplied by 8.679 plus our 0.744 gives us 18.102 Kelvin per watt. So this has got our total resistance. Now the temperature drop of the system can be determined by the ratio of the contact resistance against the overall. And so what we can say here is that we have the contact resistance, so delta T contact, will be equal to the resistance of the contact divided by the total resistance multiplied by the total temperature change of the system. And so we have it's 100 degrees Celsius, and so the change at the contact is 4.13 degrees Celsius. Now, because it's multiplied by 100 degrees Celsius, if we were to convert this to percent, it would work out at 4%. So we lose 4% of our heat through the contact with the two materials. So the two bars together, we lose 4% of the heat. And so that's how you would go about solving those types of problems. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept of thermal contact resistance, the distinction between series and parallel systems, and designing and modelling using the energy balance principles for these types of problems. If you liked this video, please consider liking and subscribing to the channel. It really helps us reach as many chemical engineering students as possible. If you'd like to connect with me on LinkedIn and get in contact, then please feel free to scan the QR code and reach out if you have any questions or want to collaborate on any problems that you may have. Thanks for watching, and we'll see you in the next video.